For tonight's TechXploration, I'm thrilled to introduce somebody who doesn't need any introduction, which is James Gosling, also known as the father of Java, and having done a lot of things over the years. So those who know, he received his BS in computer science from the University of Calgary, and then he received his PhD from Carnegie Mellon. And he was at Sun Microsystem for a number of years as a technology, as a VP and fellow in the Sun Labs, and that's where he really designed Java. He did a lot of different things there with tools, but really had a massive impact there and on the entire industry. So we're super glad to still be benefiting from that. Thank you. And then we spent some time at Google, and now he's currently at Liquid Robotics, where he's doing a lot of things, and he's gonna share some of his thoughts and insights. So thank you for joining us tonight. So,
hi, happy to be here. This is going to be kind of a weird talk for most of you folks because it's often a completely different universe. Different universe for you folks, not quite as such a different universe for me, since a long time ago I sort of started in the software business as a code monkey for a bunch of physicists. And so, working for a bunch of marine biologists is almost the same thing. It's, people that wave their hands a lot, and when they write code, it's really bad. Anyway, so I've been working at this company called Liquid Robotics for a couple of years, well, a year and a half now. And they're an interesting company. What they're trying to do is measure what goes on out in the universe. And why do we care about it? Because the oceans are most of the oxygen that we breathe, and it really determines our weather. It's going to drown most of New Orleans in, by 5:30 tomorrow. And yet, we have almost no data on it. So the real proposition for Liquid Robotics is, what if we could make the ocean data dense and cheap to do things like help us predict hurricanes? This company started rather strangely, and I had hoped to do a demo right about now, except that it seems like there's a dead server on the coast of Kona. We have a bunch of wave gliders off the coast of Hawaii that do nothing but monitor whale song, and this is whale season. And so, if you go to jupiterfoundation.org, you'll find a link, and you can stream, real-time live whale song, and it comes off of one of our wave gliders. And the company really got started in 2005, really by a guy named Joe Rizzi, who was an early guy at Fairchild. He was a VC for a long time, more money than God, big house on the coast of Kona. Sitting on the lawn, watching the whales leap, right outside his window, and wondering, why can't I listen to them? And so he decided what he wanted was like a way to, get a microphone out there, which he tried all the obvious geek things of rowing out with a microphone and a long wire, and discovering why that didn't work. He discovered why a lot of different things didn't work, and at some point he decided that what he wanted was kind of an RC car for the ocean. And then with a friend of his, Derek Hine, and Derek's son, Roger, they sort of cooked up this kind of weird robot. And then after actually getting kind of the basics of it to work in 2007, they decided to try to turn it into a company. And so that's where I am now. So it's not your average robot. Most people think of a robot as something that's got arms and legs or whatever, shows up in a science fiction movie or something. This robot is much, much simpler. It looks a lot like a surfboard. Then there's this umbilical cable, and then there's this weird thing down below that's got these funny wings. And so how it works is that the floating body goes up and down in the waves, and when it pulls the rig with the wings upwards, the little wings sort of rotate down, and they get pulled, and it goes forward, and then when the wave goes down, the winged thing at the bottom, the glider, sort of goes down and it gets forward thrust. So this thing just sort of bobs up and down in the waves, and it gets thrust without any motors, any requirements for power. It's this really, really simple mechanism to generate thrust. So how do you go from thrust to an interesting observation platform? Well, that's sort of the electronics that are on the float. One of the interesting things about this thrusting mechanism is that you can't turn it off. You know, the robot can't actually stop. You know, the closest thing we can do to stopping is just doing donuts in the middle of the ocean. And they tend to do donuts a lot. You know, if they're parked underneath a hurricane, they'll just sit there doing donuts as excitement happens around them. But they get several hundred pounds of thrust, which is quite a lot. They can tow quite a bit. They don't go very fast. They go about 1.5 knots, kind of the speed of a pleasant stroll, but they never stop, right? So crossing the Pacific is not a big deal. Crossing the Atlantic is not a big deal. Driving out to the middle of the Atlantic and doing donuts or zigzagging across the Atlantic or all over the Arctic Ocean, all of those things actually work pretty well. And it's this fact that it's got this incredible source of energy in the waves for thrust that makes the whole thing work, because it doesn't have to have like some huge power source to keep it moving. It just goes. So there are all kinds of electronics that go on the top. You can mount weather stations. They typically all have weather stations. They'll often have wave sensors. This thing right down here is something called an ADCP, or an adaptive Doppler current profiler. It's for it's kind of like an optical mouse for water. And you can put cameras on them and all kinds of things. So these robots are really platforms for sensors. You can bolt all kinds of things onto them. And often they'll actually be dragging other things behind them, things like hydrophones, things that you want to have stable in the water. You can put all kinds of interesting things on them. And one of the important things is that there's this little thing down here is the rudder. And that's the only thing that moves. It's the only thing that the computer can mechanically affect, right? There are no arms, no nothing, right? There's the little wings, they're just on pivoted hinges with springs. There's almost nothing that can break on this thing. They're incredibly robust, which turns out to be a really, really big deal. If you look inside the float, there's a bunch of watertight boxes with wires in between them. The box that's in the middle is something called the command and control dry box, and then the other boxes, you put different kinds of payloads in them, which are pretty much exclusively electronics that then have wires that connect down to whatever the sensors are. And then there's wires that go down the umbilical and they connect to the rudder, and if there's something down below that's a sensor down there, it will be connected. So all the batteries and the compute is in the CNC. On top of the glider is some solar cells. So the solar cells are used to power all the electronics, and all the thrust comes from the glider mechanism. We do all our communication through the Iridium satellite network. If we happen to be close to shore, like within about 5 miles, we can use cell phones. But we're almost never within 5 miles of the shore. We're almost always like way the hell out there. We're usually hundreds and hundreds of miles from anything. And one of the difficult things, one of the things that really rules almost everything in the software architecture side, on the ground side, is that the communication cost for us is $1 a kilobyte. Think about network protocols and $1 a kilobyte, right? When you're spending 1/10 of a cent for every byte, you think about how you encode packets differently. You think about what you send back and forth differently. We really, really, really don't have a big data problem, right? You go to Fry's, you buy a standard desktop drive. It's like 3 terabytes. It will cost us $3 billion to fill up our first disk drive, right? So at about the time we fill up our first disk drive, we can afford our own satellite constellation. And that's not going to happen. So the way that we think about stuff is a lot different. But on the other hand, while we may not have a whole lot of data to fling around, we actually care about it a lot. So we really can't afford to lose anything. And since it also contains like all the command and control information, and we often need to know where the craft are with pretty high precision, because if there's like an imminent collision happening, the pilots kind of need to know. And so while we don't care much about the volume, we care about the timeliness, and we really care about the reliability. Because if we just had like one data center and the data center went down, then we've got killer attack robots running loose with laser cannons. Fortunately, none of our guys are big enough to carry anything interesting that way.